Welcome to the final lesson in the electrical circuits unit. As you'll see, we're looking at field theory today and linking it to non-contact forces. This lesson looks at non-contact forces and field theory, and it might seem like a bit of an odd lesson to have at the end of the electricity topic, but I quite like to teach field theory by bringing all three fields together in one place. I think it makes it easier for people to make the links between the three ideas. So although I'm putting this lesson at the end of the unit on electricity for triple science, it also includes a little bit of what we learn in forces topic and also in the electromagnetism topic, and both those topics are on paper 2. In physics terms, a field can be thought of as the area around an object where another object can experience a force. And because they don't have to be in contact, we're calling them non-contact forces. So for example, masses experience a force if they're in a gravitational field. So as an example, if I were to climb to the top of a tree and jump off, I have a mass, and that mass will experience the force of gravity, and I will accelerate down towards the ground. So by having my mass in the gravitational field of the Earth, then it experiences a force, and that direction always brings me down towards the ground. In the example of me jumping out of a tree, I don't have to be in contact with the Earth in order to feel the force of gravity. And it's the same with magnets. We know that magnetic materials experience a force if they're in a magnetic field, but they don't have to be touching the magnet. So if I place a paperclip near to a fairly strong magnet, it will be drawn towards the magnet. So it doesn't have to touch it, but it will still experience the force. The third field we look at is what we call the electric field, which is where electrostatic forces are felt. So a charged particle will experience a force in an electric field. And as you can see on the diagram there, whether it's a plus or a minus will determine what will happen. So for example, a positive will attract a negative charge, whereas two positives or two negatives would repel each other. And we can see a similarity there between the electric field and magnetic fields, because we know from primary school even that if you have two norths or two souths come together, they repel, whereas a north and a south will attract. So here we're looking at a practical we often do in lower school or sometimes even in primary school, where we've shaken some iron filings around a magnet and we get a pattern rather like the one shown here. But what is this iron filing pattern actually showing? The iron filings are lining up along the field lines, which we also sometimes know as flux lines. They show the direction that magnetic material moves in the magnetic field. If we think back to the gravitational idea where I was jumping out of a tree, then we know that I would move directly down towards the ground. And in this example with the magnetic field, this shows the direction that something would move as it comes towards or is attracted, or goes away, is repelled from the magnet. This idea of direction is really important when we're looking at field theory. When drawing out magnetic field lines correctly, we have some rules we always have to apply. The first one is that the field lines always go from north to south, and therefore we have to draw arrows on those lines to show the direction. So you'll see that they're going from north to south, and at the North Pole they're coming out of the north and away from north, whereas on the South Pole they're coming into the south. The field lines must also never cross, and you'll see here that on the diagram they've been very careful not to allow the lines to cross. So what would the field lines around these two magnets look like? You can pause the video and see if you can work it out for yourself. Try applying the two rules. The field lines must always go from north to south, and they must never cross. So here's the answer. And in fact, I could kind of add in these lines here and just show that actually these would join up around the outside. That's not very beautifully drawn, but you get the idea. And therefore, you could draw the field lines all the way around. We sort of run out of space a little bit here. But the key point here is that everything's gone from north here to south here, and at no point do any of these lines cross. You do end up with a point right in the middle between the two magnets where there's a sort of neutral point, And at that point there is no force acting, so you can see that the magnets are pushing away and you've got that little null point left in the middle. So have a think about this second example. Perhaps pause the video and see if you can work out the answer. Remember, the lines always go from north to south and they mustn't cross. And so here's our answer. And this time you can see that there are a lot of lines bunched up between the north and south. And that's where we've got that very strong attraction where those lines are very close together. Now we can also draw in gravitational field lines to show the direction that a mass would move in a gravitational field. So we know that any mass would fall directly down to Earth, and therefore all the lines are going in towards the Earth. And the arrows are pointing in because that's the direction a mass would move. So in this diagram we're asking the question, what would the field lines look like if we're close to the Earth where it appears flat? Now we know the Earth is a sphere, but to us, to all intents and purposes, it appears flat. And again, we'd have to draw the lines showing the direction a mass would move as it came towards the Earth. And so from a sort of flat perspective, then everything would appear to fall straight down. And so near to the Earth, we say that a gravitational field is close to being uniform. So it's all uniformly spread out, like in this diagram. So our third field is the electric field. And again, we can draw field lines to show the movement of a charged particle in an electric field. The rules here are that field lines always go from positive to negative. So not north to south, but positive to negative. Again, we must always draw arrows to show the direction, and the field lines must never cross. If we look at the example on the left, that's a point source. That's just a little bit of charge. So that could represent a positively charged particle like a proton. It will have an electric field because it's charged, and that's the direction of the field lines. They will be going out from positive. On the right hand side, we're looking at a negatively charged particle. That could be an electron. It has an electric field because it's electrically charged, and the direction of the field must show the direction that something would move, and in this case we're showing the arrows going in towards the negative. So like with the magnetic field examples we looked at, what do you think the field lines will look like between these two positive charges? We know that positive charges will repel each other, and we know the rules are that the field lines go from positive to negative and they must never cross. Have a think about it, pause the video, and then in a moment come back and look at the answer. So here's the answer. You can see our two positive charges, and you can see that all of the field lines come out of the positive charges and away to some negative charge somewhere in the distance. You'll also see that rather like the magnet example we looked at earlier, we've got this sort of odd bit in the middle here where there are no field lines that we call the null or neutral point. And the repulsion of those two charges has pushed those lines away and left that blank space in the middle. Let's see how you do on the next example. So this time I've got the same thing, two like charges that are going to repel each other, only this time they're negative. So will the diagram be the same as the last one, or will there be any differences? So as you can see, the answer looks almost exactly the same, but there's one key difference, and that's the direction of the field. And as you can see, it's going into the charge, not out. Because these are negative charges, and electrical field lines always go from positive into negative, we have to draw the arrows the other way around. So how about the electrical field you'd see between a positive and a negative charge? Again, the rules are the field lines go from positive to negative and they must never cross. Do you think there'll be a parallel here with the magnets when we had a north and south pole? So as you can see, the answer looks really similar to the magnet one, only this time we've got a plus and a minus rather than north and south, but the lines are always going from positive to negative, and we also end up with this bit in the middle here where the lines are really quite close together, and that's where the region of strongest attraction is going to occur. So with electrical fields, we can also have uniform electric fields. So rather than having a point source, you could have a plate like this. And in fact, we use these in components called capacitors. What does it look like if I tip the diagram on its side? So in this diagram, the uniform electric fields looks really like a uniform gravitational field. And that's because the shapes of fields are very similar. It doesn't really matter whether you're looking at an electric, magnetic or gravitational field. Now with magnets it's harder to see the uniform field, but actually that region between the north and south when they're attracting can get very close to being parallel and uniform. What's more difficult is to imagine a point source magnet. So whereas we could have one planet representing a point source of gravity, and we could have a charged particle representing a point source of charge, we don't tend to have what we call unipole or point source magnets. So here's a question. Thinking about the fields, which of these three do you think is the odd one out? Again, I'll give you a moment if you want to pause the video to think about it before we look at the answer. A lot of people are surprised by the answer gravity. We tend to assume we know a lot about it because we've been aware of it for such a long time. Certainly we've had a good idea about how it works since Isaac Newton's days. However, there's still a lot to learn. Gravity only attracts, it doesn't repel, which is unusual as a field because magnetic and electric fields both attract and repel. It's also very weak. And that seems a surprising statement because we think about ourselves being attracted by the gravitational field of the Earth. But of course the Earth is massive. Literally, it's got a lot of mass. So its gravitational field compared to us appears very, very strong, and we are attracted to the surface of the Earth. But anything with mass has a gravitational field, and that includes you and me. It's just that our gravitational pull is so tiny we would never notice it. Gravity also acts over huge distances. So the Sun keeps the Earth in orbit around it due to its gravitational pull, and that's 150 million kilometres away. And of course we're aware that there are planets far beyond Earth which are affected by the Sun's gravitational pull, and of course our solar system is part of the Milky Way, and we are kept in that galaxy by gravitational forces. If you're thinking about gravity being weak compared to magnetism and electric fields, think about sticking a magnet on your fridge. The magnet is really small, and yet it overcomes the gravitational force of the Earth to stick to your fridge. So that magnetic force is much greater than the gravitational force trying to pull it down onto the ground. But that magnet won't act over huge distances. Even a pretty strong magnet is only going to act over a few centimetres at best, unless you're buying something very specialised. It's certainly not going to affect the orbit of Pluto. So that's the end of this little lesson. It's not a typical lesson because I have gone over 3 different units, but I hope you found it interesting and useful to think about those 3 different fields all together so you can see their similarities and their differences.